Hello and welcome to my presentation on the topic as shown in the screen, which is a review of 10-year trend in system design and technology advancement of plant-based agri-food smart and sustainable indoor farming in the bracket passive towards carbon sink and future resilient smart cities. I am Dr. Diana Mohamed Nasir, a lead investigator for a British Council's International Science Partnerships Fund Global 2 Challenge 2024. I'm also representing our research collaboration under the team of 5, which includes Dr. Ali, Dr. Ismail, Dr. Sohaimi, and Professor Hughes. I'm also representing the School of Mechanical Aerospace and Civil Engineering, the University of Sheffield, UK. So this is the structure of my presentation, as you can see from the screen. I would like to start with the fundamental behind sustainable food production and what is this meant for. Figure 1, as you can see, demonstrate the fundamental of sustainability, which has 3 main elements need to reach, which are preserve the ecosystem in our environment, ensuring economic feasibility, and also continuously cultivate social growth in multiple aspects. Estimated from the United Nations, there will be a rise in global population from 8 billion to almost 10 billion by 2050. And now we are facing unpredicted climate change, natural disasters, pandemic, and geopolitical interventions. So all this somehow cause significant challenges for us to practice conventional agriculture in order to address food scarcity and resource depletion issues. UNFAO also highlights several factors to sustain food production, including effective cost overproduction without jeopardizing the ecosystem, prioritizing on health crop, and also mitigating resource depletion. To address this, sustainable food systems should be able to be resilient by adopting resource efficiency and also the use of circular economy. Through implementing sustainable agriculture in cities, there are several benefits in regards to environmental challenges that can also be addressed, including minimizing power consumption, optimizing resource use, and also reducing greenhouse gas emission. As the figure 2 diagram, we began our review analysis on smart indoor farming based on thematic procedure, which we focus on filtering documents with these 5 keywords. They are indoor farming, smart, technology, food, and also carbon. We only retrieve open access articles and proceedings from the webs of Science, Science Direct, and also Dimension AI. We then excluded these 4 keywords, which are aqua, animal, poultry, and also fish, to focus on plant-based indoor farming cultivation. With this, we retrieved 204 documents, but then we excluded another 38 documents because of duplication and also non-English spoken writing. We finally selected 166 research articles and proceedings. After finalizing the papers, we then uploaded these papers into Mendeley Reference Manager to obtain .ris file, which then we use this file and upload it into VOS Viewer in order to run a bibliographic analysis based on these papers and also to extract the most occurrence keywords in the papers with a minimum of 4 numbers of occurrence. So this software managed to extract the top 20 most occurrence keywords. But because of there are duplications in some keywords, we are forced to eliminate another 5 keywords. So if you look at this figure 3, you can see all these keywords are grouped in 4 colored clusters. What we found is that the most occurrence keywords are vertical farming, urban agriculture, sustainability, Internet of Things, and also plant factory. Then out of the total 166 articles, we found 54 open access review articles within this 10 years gap between January 2016 and January 2025. From these review articles, we discovered a list of keywords which occurred at least 5 times. Through these settings, there are 55 keywords listed to have occurred more than 5 times in all these documents. 22 generic and irrelevant keywords to passive system had to be removed. So the total of 32 keywords were finally retained, and they are grouped in these 5 colored clusters. So this group highlighted the correlation of the clustered keywords that collided to one another in the document. So you can see that from the figure 4. With the bibliographic analysis, according to our thematic procedure, we then formulated our aim, which is to address potentials and challenges in enabling plant-based agri-food smart indoor farming or passive systems as a major alternative or technique to sustain future plant-based agri-food production in large scale in replacing conventional open field crop farming practices. There are 2 objectives to achieve the aims, which are to retrieve, review, and analyze the trend in system design and technology advancement involving indoor farming systems over the past decade. The second one is to review the feasibility of the technological trend in terms of economic sustainability and public perception towards its large-scale implementation, so that it can provide a decent, realistic insight of how future resilient smart cities embarking carbon sink strategies can be shaped. We also formulated our research questions, which are the first one, what are the key drivers towards realizing an efficient passive, and how can they further transform passive for smarter, sustainable urban infrastructure practices? The second question is, what are the required measures to improve the existing passive design and technologies to advance these solutions for future large-scale agri-food production, adapting climate-responsive and resilient approaches? Followed by the research questions, this review was managed by overviewing a dynamic correlation between passive and 3 main subtopics. So they are large-scale agri-food production, system design development, and also technology advancements. These keywords are, these key subtopics are inspired by the most accurate keywords in the retrieved documents of vertical farming and its links. There are another 5 subtopics to be added, which are economic feasibility, community-based agriculture, decarbonization, smart city, and also resilient city. So these are formulated to advance this review according to the second and third most accurate keywords of sustainability and urban agriculture, and with their interconnected links. So now we will try to comprehend the concept of smart indoor farming. So this concept aims to transform future cities into agri-food hubs, coming from the advancement of farming engineering and technologies. So its fundamentals has taken inspiration from the UN FAO's 4-pillar model of food security, which are enough food with right quality, accessibility to available resources for high quality food, sustainability in nutritious food supply all the time, and also to utilize food to reach a state of nutritional well-being. There are 3 main architecture components of smart indoor farming for urban scale application. The first one is the environment must be designed under controlled behavior. Second one, the system should be built for automated control. And the third one, it should be designed to allow multi-scale, can produce in mass volume, should strive for time saving, and should be more efficient than the conventional farming practice. As you can see from the screen, smart indoor farming technologies are going for maturity over the years through continuous innovation and R&D since the last 30 years. So under controlled environment, starting from just a conventional greenhouse with manual handling, then to include sensors, actuators, hydroponics. Then there are improvements in the irrigation and fertilization, use LED lights, include PV panels for energy harvesting, and then now we can see aeroponic sprinklers, fogponics, and also photoperiod treatments. Under automated system, it started with just having Wi-Fi network, including electronic control modules. Then it evolved to Internet of Things, deep learning for image processing and precise management, then moved to machine learning for predictive performance capability, and last one is cloud-based digital twin platform for both precise management monitoring and also predictive analysis. To scale up the system, so the latest innovation have evolved from just a normal modular rack structure to have rotational components and adjustable components. Also, there are the R&D on crop genomic modification and microorganism enrichment, and the latest one is to harvest biomass and biogas energy from the waste produced from the indoor farming. From our review, we found that the tested crop with smart indoor farming are categorized into 3 categories. So the first one is vegetables, herbs and fruits. Second one is cereal or grain or legumes and wheats. And the third one is edible and non-edible flowers. For the first category, the most studied crop from the review was lettuce, while other types like herbs, pak choy, kai lan, kale, fruits, and also chilies were mentioned. For the second category, despite the researchers could not agree the suitability of this type to be grown using smart indoor farming techniques, we still found that the most studied crop was paddy or rice, followed by wheat. And the third category, because there is a rising demand to cultivate medicinal and ornamental plants, we found begonia flower, sunflower, and safflower are mostly mentioned in the documents. So now we move to main component designs, which we highlighted of its maturity under 10-year publication. We will start with under control environment. So in our review, we categorized the review beginning with the innovation involved with the grow house design, from small scale to larger scale implementation, such as grow off, polytunnels, and also agrivoltaic agrotunnel systems. Then we reviewed different types of hydroponic system designs, which are categorized as ebb and flow, nutrient flow or NFT, deep water culture, wick, and also drip. We also reviewed the 3 innovations of aeroponic systems, which are based on water sprinkle technique of low pressure automation, high pressure automation, and also combined aerohydro system. Then we touched on fogponic system, which use fogging as irrigation systems, including the conventional one and the one built up set with the LED lighting. We also reviewed different strategies for irrigation and fertigations, plus innovation involved on thermal, cooling, and ventilation components of smart indoor farming. Also, we touch on the sensors and actuators used for smart indoor farming as shown here. Under technology advancement, we began our review on different strategies of combining and programming IoT, microcontroller, and software applications. This included to review different types of wireless sensor network involved with smart indoor farming. We then reviewed the advancement in precise management and monitoring techniques, including deep learning combined with optical sensing and image spectroscopy, use of 3D scanner and combined programming with linear motion guide and image acquisition system. Under predictive analysis, we reviewed some prediction modeling techniques such as MLP2 and CNN. These two are machine learning algorithms and usually are operated either under TensorFlow, Python, or other cloud-based systems. We also include our review by highlighting advancement in multi-scaling the system through enlarging the implementation via modular design, racking system, adjustable system, hanging design, and also motion conveyor operations. We also touch on innovative approach on optimizing the use of artificial light and photoperiod stress treatment on crops to achieve healthier and high quality growth. These included manipulation and combined different exposure and colors of LED lights to crops. We finally reviewed the innovative genomic modification techniques, which are also meant for achieving healthier and high quality growth, including enriching microorganisms, mix of substrates, and also adopt dynamic dosing of iron concentration. In this review, feasibility analysis of smart indoor farming on 3 factors associated to financial, economic, environmental sustainability, and social attitudes are made important. So under financial economic feasibility, we found that there are still obstacles in gaining profits from smart indoor farming because of no one-size-fits-all indoor farming projects, which this lacks financial data of costs, risks, labors, and yields that can be retrieved from actual case studies. From some research, there are some key aspects being highlighted to increase the profit margins, including minimize capital costs through maturing technology, enhance labor efficiency, scale operation with fixed costs, and also reduce costs on rent and electricity. Studies also highlighted the importance of considering combining 2 or more sustainability measures between government-led sustainability, consumer-led sustainability, and market-driven sustainability for a feasible profit decision and cost optimization. Under environmental sustainability and carbon life cycle, so there are studies which highlighted the successful large-scale implementation to be achieved by synergizing water, energy, and food sectors to enhance the complementary between these sectors, such as through recycling and reusing the waste from indoor plant factories for biomass and biogas energy harvesting, while water recycling plants shall be able to be designed altogether with indoor plant factories. Some studies found a promising future under green tech sector and industries, which will create large-scale new job opportunities with high-demand skills on AI. This can be done by synergizing circular economy, agriculture, with advanced engineering, software engineering, technologies, renewable energy, building construction, and urban planning sectors. Through adopting circular economy concept, smart indoor farming can be designed in adaptive approach, including smaller the scale for plots of land, for example, if they are too expensive to purchase, as well as adopting low-cost energy technologies. Other researchers also emphasize to adopt modular-based circular economy principles for large-scale operation of passive or smart indoor farming by designing the operation system to respond fast and easy with automation capabilities. This include training the system to be adaptive to efficient identification on sorting items, mitigating blockage, and also assessing risks. Under social perception or attitude, the review found there is a mix of social attitudes on how communities understand the aspiration behind the drive on indoor farming and also how these communities can take up roles in supporting the potentials underlying its large-scale implementation. But we also found that there are high demands movements of adopting sustainable urban agriculture as a natural therapeutic process for individuals. Some techniques such as principal component analysis combined with 2-step cluster analysis were used to identify key attitudinal components as well as segmentize consumers into being skeptical, open to indoor agriculture, supportive towards indoor agriculture, and engaged with indoor agricultures. This led to a little bit of negative attitude from respondents because of lack of knowledge on indoor agriculture. Another technique through interviews, workshops, and dialogue sessions with residents and also businesses, highlighting or promoting community-based urban farms somehow receive more positive reaction. This is particularly with community outreach and educational programs being organized. For our final highlight, we can conclude that the technology advancement of passive system does bring a huge impact to regenerate the food security of the future by implementing it in large scale. But financial feasibility, environmental sustainability, and also social attitudes are the key factors to consider beforehand. On financial feasibility, standardized economic feasibility model is the most crucial one, including to the support from the government's policies on sustainable agriculture, as well as funding and financial incentives to promote green economy for creating new job opportunities. On environmental sustainability and carbon reduction, symbiosis of sustainable agriculture with waste recycling, bioclimate design, and also decentralized green energy harvesting sectors are the most promising one. Plus, integration of low carbon cooling, heating, and ventilation strategies will further drive off the high use of energy from passive system. On social attitudes, strengthening the promotion on awareness of smart indoor farming is the most important one, with the support from local councils in approaching neighborhood communities through the influence of social media and also mobile apps. The collaborative approach between communities and local retailers will escalate the domino effect of passive implementation. On the technology advancements, so advanced computation, data analytics, AI-driven techniques, digital twin, predictive modeling, and adaptation of modular and circular economic design on the controlled environment systems will definitely help to strive the world commitment in meeting with the Industry 5.0. Before we end this session, we would like to express our gratitude to the British Council's International Science Partnership Fund worth of around £158,000 awarded to me, representing the University of Sheffield in collaboration with Malaysian lead partner Dr. Ali, representing University Putra Malaysia, and two Malaysian associate partners, Dr. Ismail of University Technology Malaysia and Dr. Sohaimi of University Utara Malaysia. Our innovative project is titled as Paddy IoT, Community Prototype and Monitoring of Real-Time Agri-Paddy Hydroponic System Integrating Controlled Air Capture. Some references relevant to the research that I've just presented. Again, some references relevant to the research. Thank you very much for listening. If you have any query or would you like to collaborate with us in relevant to our research, you can drop me emails to the detail as displayed here. Thank you.